Hi everybody, this is Mikhail from AUA with probability lecture number 37. And today we're going to talk about simple concentration inequalities. In particular, we'll talk about Markov's and Chebyshev's inequalities, and we will consider also very important limit theorems. We'll talk about the law of large numbers and the central limit theorem. So first about Markov and Chebyshev inequalities. We have learned so far how to work with random variables by having their complete characteristics, by having their CDF or PDF or PMF. Say, we know how to calculate probabilities like this, the probability that X will be in interval AB. If we have the CDF, say if we have the CDF, this will be the value of CDF at B minus the CDF at A if our CDF is continuous. Otherwise, we will take one-sided limit. Or we can calculate this probability if we have, say, the PDF. X is continuous and we have the PDF. Then we will, to calculate this probability, we will integrate the PDF from A to B, and we will get this probability. Now, also we have talked about the following, that in practice we do not have, most of the times we do not have complete characteristics of random variable X. We just have partial characteristics, expectation and variance, mean and the variance. So nobody will give us the CDF, nobody will give us the PDF or PMF of random variables. Instead we will have the mean and the variance. And a problem arises whether we can calculate this kind of probabilities having only that partial information, having only the mean and the variance of a random variable X. Of course, we cannot calculate. Knowing only the mean and the variance is not enough to calculate probabilities like this. And this is because we can have different random variables, in fact, infinitely many random variables with the same expected value, with the same variance. And for each of them, we can get different values for these probabilities. And you can try to give some examples of that type. Fortunately, it turns out that having only mean and variance, we can maybe not calculate, but we can estimate this kind of probability. We can say something about that probabilities. For example, our concentration inequalities estimate how concentrated are the values of our random variable around its mean. And Chebyshev and Markov inequalities are inequalities of that type, basic types of that concentration inequalities. And in fact, Markov inequality is estimating the tail probability of a random variable. And today we're going to talk about that two inequalities. First, we will consider Markov's inequality. We will assume that we have only the expected value of that random variable X. We have only this number as an information about X, and we will try to estimate this kind of probabilities, to say something about probabilities about X. So this is the Markov inequality. If X is a random variable, which is non-negative, and A is some positive number, then the probability that X is larger or equal than A, this is the tail, and this is the tail probability. So the tail probability is less or equal than the expected value of X over that A. And this holds for any positive A. This holds for any non-negative random variable X. So proof is simple. We introduce a new random variable Y, which takes two values. It is A if our X is larger or equal than A, and it is 0 otherwise. So Y is discrete, it takes only two values. Y is the transform of X, if you want. And it is easy to see that Y is less or equal than X for any case, for any omega. Why is that? So we can consider two cases. Say X is less than A. In that case, Y will be, if X is less than A, Y will be 0. If Y is 0, here we have 0, and here we have non-negative number, because non-negative value, because X is non-negative always. So this will be correct in this case. In the second case, we will have we will consider this case x is larger or equal than a. Then this will be x and this will be a. If x is larger or equal than a, then the value of y is a. So we will have x is larger or equal than a, and this is correct by our consideration, because we are considering this case. So always this will be true. If that is true, then the expected value of y is less or equal than the expected value of x. And the expected value of y is easy to calculate. Y is taking only two values, 0 and a. A is when x is larger or equal than a. So a times the probability that it is taking the value a. It is taking the value a. This is when in the case when x is larger or equal than a. So and 0 otherwise. So I am not writing that 0 times the probability that x is less than a. So this is the probability. If you will plug this here and divide by a, you will get exactly the Markov's inequality. Note, in Markov inequality, it is important that x is non-negative. Say, if x is a random variable taking both negative and positive values with expectation equal to 0, then the Markov inequality will not be correct for that case. Why is that? Because let me write the Markov inequality. So probability that x is larger than a, this is less or equal than the expected value of x over a. So if this is 0, we will get 0 here. So we will have the probability that x is taking values larger than a is less or equal than 0. The probability cannot be less than 0, so it will be always equal to 0. So probability that x is larger than a is always 0 for any positive a. So this means that x is not taking positive values. But I was talking about the case when it is taking both negative and positive values and the mean is 0. So the Markov inequality will not be correct if, in general, if x is taking negative values. So it is important to use Markov inequality if we have non-negative random variable. Okay. So if we want to use Markov inequality for any random variable taking both positive and negative values, what we are doing, we are plugging instead of x in our Markov inequality the absolute value of x. So we are using Markov inequality for absolute value of x. If I will write instead of x the absolute value of x, this is non-negative, so I can use that. So the probability that absolute value of x is larger or equal than a is less or equal than the expected value of the absolute value of x over a for any random variable x and for any positive number a. Okay? So Markov's inequality is informative only if a is large, if a is larger than expected value of x. Otherwise, this is trivial because if a is smaller than expected value of x, then this is larger than 1. So we will have something like this. Probability is less or equal than, say, something that is larger than 1. Well, always we have that probability is at most 1. So this is not giving any information. This inequality will give some information if a is larger than expected value of a. So sometimes people are writing Markov inequality in the following form. So this is our Markov inequality. If instead of a, I will take a times expected value of x. So instead of this, I am taking that. So here I will take a times expected value of x, and I will have expected values cancelled. So Markov inequality can be rewritten in this form. And let me just explain interpret what this means. This means that non-negative value if we have non-negative random variable, then the values that the probability that values of x will be far away from much larger than the expected value is small. So the probability that x is taking larger values than our expected value is small. It can be estimated by this 1 over a. Sometimes people are writing Markov inequality for this kind of probability. So if this holds, then if I will pass two complements, the probability that x is less or equal than a is larger or equal than 1 minus expected value of x over expected value of x over a. Here I need to write smaller than a. Well, I will correct that. Okay, I need to have the correct is to write this is less than a. Okay. So Markov's inequality is giving us tool to estimate probabilities like this if we know only the expected value of x. One example, let x be the wage of randomly chosen working person in Armenia. So average salary. We know that the average salary, well, x is the salary, sorry, and the average salary is this much, 190,000, I mean in drams, in this first quarter of this year. This is from Armstat webpage. So then the proportion of persons receiving more than 10 times that average is not more than 1 over 10. This is a simple consequence of the Markov inequality. So probability that x, our random salary of a person, will be 10 times the average is less or equal than the expected value over this 10 times average. So expected values will be cancelled. This is less than 1 over 10. So the proportion of wages larger or equal than 10 times the average, so 1,900,000, will be less or equal than 1 over 10. And this is from Wikipedia. By the Markov inequality, no more than 1/5 of the population can have more than 5 times the average income. The same as my example. Now, we give the Chebyshev inequality. The next important inequality is the Chebyshev inequality. Now, we assume that besides the expectation x, we know also the variance of x. So we have more information about x. Then, having more information, we can estimate probabilities more precisely. And this is given by Chebyshev inequality. Assume x is any random variable, any signed random variable, and let a be a positive number. Then the probability that x minus expected value of x in absolute value is larger than a. So this means that the probability that deviation, absolute deviation, is larger than a is less or equal than the variance of x over a squared. So first, about the proof. Proof is very simple application of Markov's inequality. So let me write the following. Our aim is to calculate this. Expected value of x is larger or equal than a. So I'm writing this in the following way. The probability that x minus expected value of x squared is larger or equal than a squared. Well, this is the same as that. And now I'm using Markov's inequality. So Markov's inequality is for any non-negative random variable. This is non-negative, so I can apply that Markov. So Markov inequality is giving this is less or equal than the expected value of this, so ratio, expected value of x minus ex squared over this number, which is a squared. And the expected value of x minus ex squared is just by definition the variance of x, and this will give variance of x over a squared, what we have here. So simple. And we can rewrite our Chebyshev inequality in this form. So if I will plug instead of a times standard deviation of x, so here I will have this part, so on the left side I will have this, and on the right side I will have variance of x over this squared times this squared. So I will have a squared times standard deviation squared, which is the variance. I will have that variance cancelled, and I will be left with this 1 over a squared. So this is another version of our Chebyshev inequality. And sometimes people are writing Chebyshev inequality with this smaller sign, so passing to complements. So probability that this is less than a, so the deviation, absolute deviation is less than a, is larger or equal than 1 minus the variance of x over a squared. So Chebyshev's inequality says that we can estimate the probability that x takes values away from expected value by its variance. So if variance is small, variance of x is small, then the probability that x will be far from expected value of x is small. So if variance is small, then the values of x will be concentrated around that expected value of x. Well, this is quantitative estimate for that, what it means that values are concentrated around that expected value of x. For example, the probability that x will be more than 3 standard deviations away from expected value is, well, this is the deviation. X is 3 standard deviations away from expected value. I'm writing in mathematical form. This is that form. And I'm calculating what is the probability that x will be far from this, more than 3 standard deviations. So this is by Chebyshev inequality less or equal than that this number squared, so 1 over 9. So we have only 1 over 9 chance that x will be away from its mean more than 3 standard deviations. And this works for any random variable x from any distribution. So for comparison, we knew by the 3 sigma rule the following. If x is normal with mean mu and variance sigma squared, then the probability that x will be 3 sigma in this 3 sigma region of mu, in the mu minus 3 sigma mu plus 3 sigma, with probability almost 0.997. This is our 3 sigma rule for normal random variable. So we can write this in this form. So the probability that x minus mu is less than 3 sigma is 0.997. And if x is any random variable, here we are talking about normal, but here we are talking about any random variable. If x is any random variable with expected value mu and standard deviation sigma, then by Chebyshev inequality, the probability that x minus mu is less than 3 sigma is larger or equal than 1 minus 1 over 9, 8 over 9. So, of course, this is more precise estimate, but this is because we know the concrete distribution, the exact distribution of x. But if we do not have exact distribution, this is any random variable, we can say we will have some information about this. We will have that this probability is larger or equal than 8 over 9. So one example, assume x is a random variable with expected value 9 and variance 0.2. Estimate this probability. So x, now 8, 10. I want to find what is the probability, or estimate what is the probability that x is here. Expected value of x is 9, just the midpoint. This is the expected value of x. Okay, this is nice because I will have symmetric interval around that expected value. I can write in the form of Chebyshev inequality. So I can write this in the following form. Probability that what I'm doing in the Chebyshev inequality, I have something like this: x minus expected value of x in absolute value. Either this is larger or smaller. So to obtain something like this, I need to have absolute value of x minus 9 in our case, because expected value of x is 9. So I want to rewrite in the terms of absolute value of x minus 9. So what I'm writing, 8 minus 9 is less than x minus 9, and this is less than 10 minus 9. So I'm subtracting 9 from all sides of this inequality. And I will have the probability that minus 1 is less than x minus 9, and this is less than 1, is our probability. And I can write this in this form: probability that x minus 9 is less than 1. And to use Chebyshev inequality in its original form, I need to have the probabilities larger than something. So I'm writing 1 minus probability that x minus 9 is larger or equal than 1. Now I have the form for which I can use that Chebyshev inequality. Chebyshev inequality says that this is less or equal than the variance of x over this squared. So the variance of x. Because I have minus sign, I will have this is larger or equal than 1 minus, so let me write Chebyshev. By Chebyshev inequality, I will have this is larger or equal than 1 minus the variance of x over 1 squared, well, 1. So 1 minus variance of x was 0.2, so 0.2. Well, this is equal to 1 minus 0.2. So what I can say about this probability, this is larger or equal than 1 minus 0.2, which is 0.8. So you can see that only having this information and that information, I was able to estimate this. With high probability, I can say that x is between 8 and 10. Okay, but what about this case? So in this case, unfortunately, unfortunately, I will not have symmetric interval around that expected value 9. So I will have 10 here and 8.1 here. So this is not equal to that. So I need to do something to estimate this probability. So I can write the probability that x is here, is larger or equal than the probability that x is, I am making a symmetric interval around that 9. So I am making it from 8.1 to 9.9. So 9.9 symmetric point around, symmetric to 8.1 around 9. Now I can do the same thing as above. So I can write the following. This is equal to probability that I'm extracting 9, subtracting 9. So I will have minus 0.9 here is less than x minus 9 is less than 0.9. So I have symmetric thing. So I can write this in the form of absolute value. So absolute value of x minus 9 is less than 0.9. Now to use the Chebyshev inequality, I'm passing to complements. So 1 minus probability that x minus 9 is larger or equal than 0.9. Now I can use Chebyshev inequality for this. Chebyshev inequality says that this is less or equal than the variance of x over this squared, 0.9 squared. And because I have minus sign here, I'm writing this is larger or equal than 1 minus the variance of x over 0.9 squared. So I will have 1 minus 0.2 over 0.9 squared. So I will have this is larger or equal than this number. So I will have some estimate for this for general random variable x. Okay, so the next example is the following. x1 to xn are IID random variables with finite expectation mu and variance sigma squared, and let xn bar be the average of xk's. So x1 plus x2 plus etc. xn over n. Prove that the probability that xn bar minus mu is larger or equal than some epsilon is less or equal than the variance sigma squared over n times epsilon. So this is important thing, and we will use this inequality for the proof of law of large numbers, and this is very useful in statistics also. Let me prove this. So here I have xn bar. To use the Chebyshev inequality, I need to have something like this. Some random variable minus its expected value. And we need to have this kind of probability. Probability that y minus expected value of the same y in absolute value is less or equal or smaller or equal than some a. If this is larger or equal than a, we will estimate this is less or equal than the variance of y over that a squared. This is the Chebyshev inequality. So here we have xn bar, this random variable. Let's see that this is exactly the expected value of xn bar. So if I will calculate the expected value of xn bar, this will give, well, 1 over n will go out of the expectation because of that properties of our expectation. We will have x1 plus x2 plus etc. plus xn. And because of linearity of expectation, we will have expected value of x1 plus expected value of x2 plus etc. expected value of xn. Because they are identically distributed, then the expectation of each random variable will be the same because they have the same distribution. So all expectations will be mu. So I will have n times mu over n, and finally I will have that this is mu. So this is exactly the expected value of that. Now I can write this. So let me erase and write. Oh, well, maybe I will erase just this part. Okay. So I will have something like this. Probability that xn bar minus mu is larger or equal than epsilon. This is the same as probability that xn bar minus expected value of xn bar is larger or equal than epsilon. This is because this mu was the expected value. Now I have the form of our Chebyshev inequality. So this is y, this is expected value of y, the absolute value of this difference is larger or equal than something. So by Chebyshev inequality, I will have this is less or equal than the variance of this random variable, so xn bar, over this squared, so epsilon squared. So it remains to calculate the variance of this random variable. So let me erase and calculate the variance of xn bar now. Well, we have calculated this, but let me repeat that again. So the variance of xn bar is the variance of this ratio. So I am taking out that 1 over n. Constant goes with square out of that variance. So I will have 1 over n squared. The variance of sum x1 plus etc. plus xn. Now, because xk's are independent, here I am using independence, I will have the variance of sum is the sum of variances, variance of x1 plus variance of x2 plus etc. variance of xn. And because they are identically distributed, the variance of each xk will be the same, sigma squared. So I will have here n times sigma squared. And I will have one n's cancelled, so this will give n over sigma squared over n. Sorry. The variance of each xk will be sigma squared. So n times sigma squared over n squared, sigma squared over n. So if I will plug that value here, I will have sigma squared over n times epsilon squared. What we wanted to to get. Well, yeah, I forgot to write here squared. I will add that. So this inequality is not correct. I need to have n times epsilon squared. This is the correct one. Okay, what this will show, say that will show that this probability is going to 0 when n is tending to infinity. If we have this kind of thing, and if n is tending to infinity, then this probability tends to 0. And this is, in fact, the statement of the law of large numbers, one of the statements of law of large numbers. Okay. So the next example, assume x is a random variable, any random variable taking negative, positive values, etc. And gt is a non-negative strictly increasing function. So it is non-negative, it is strictly increasing function. We need to prove that probability that x is larger or equal than a is less or equal than this. So how to use, we need to use Markov's inequality in this case, because this is of that form. So, but Markov's inequality was for non-negative values, random variables, but x is here any random variable. So what I'm doing, because g is strictly increasing, x is larger or equal than a if and only if g of x is larger or equal than g of a. Now this is our new random variable, which is taking non-negative values. So I can apply here Markov's inequality. So by Markov inequality, I will have this is less or equal than the expected value of this, g of x, over this, g of a. And this is what we wanted to obtain. In particular, if I will write to obtain that b, if I will write this is larger or equal than that, means that e to the x is larger or equal than e to the a, and applying that Markov inequality, I will get expected value of e to the x over e to the a. Okay. So, this much about Markov and Chebyshev inequalities. Let's talk about limit theorems. So, before talking about limit theorems, let's talk about the sum and average of IID random variables, because our limit theorems will concern that sum of IID random variables or the average of IID random variables. So recall that x1, x2, etc., xn are IID if xk's are identically distributed. Say they have the same distribution, say the same CDF, or they have the same PDF, or they have the same PMF. And x1, xn are independent, mutually independent. And because all xk's have the same distribution, then they will have the same expected value and they will have the same variances. And in the rest, we will consider an infinite sequence of IID random variables. We will talk about some limiting behavior of something, of mean or the sum of them. So we will have infinitely many IID random variables. The questions we want to consider here, we want to answer here are the following. Assume we have IID random variables, x1, x2, xn. What is the distribution of their sum? Or what is the distribution of their average? So I am denoting by Sn the sum of that random variables in this lecture, and by xn bar I will denote the average of first n terms. Say x1 can be, I'm tossing a coin several times, n times. x1 is the result of that coin toss, either 0 or 1, 0 or 1, 0 or 1. If I am doing that experiment independently, then I will have IID random variables. So IID, because the distribution of that xk will be Bernoulli with probability p, which is the probability of having one side of that fixed side of that coin. So xk's will be Bernoulli, so the same distribution, and xk's will be independent if I am doing that trials independently. And what will show Sn? Sn will show the number of successes, the number of ones. So in that case, this is the number of ones or number of successes. Okay. Say if I am doing another experiment, I am asking or measuring the height of some persons. This is, I will ask, say, tomorrow the height of some n persons I will meet. So x1 will be the height of the first person I will meet, x2 is the height of the second person, etc. xn will be the height of nth person. The heights are independent, so I will have the sum of independent random variables. If I will assume that all heights are coming from some fixed distribution, then xk's will be the distribution I do not know, but they are coming from the distribution of all heights, say. So xk's will be identically distributed and independent, so xk's will be IID. And what this will show in that case? This will show the average height of that persons I will meet tomorrow, say. So we can talk about the sum in one context, and we can talk about the average in another context, and we can talk about that sum of IID random variables, average of random variables by using that limit theorems. Let's see what we can say about the distribution of Sn and Xn bar. But first, what we know about this and that, besides that limit theorems. Well, as you remember, calculation of distribution of the sum is not an easy job. Well, we need to calculate some convolutions. So if we want to calculate the distribution, if we want to find the distribution of this is very hard. Very hard to find the distribution, and usually it is impossible to find that distribution. But for some cases, we have answers for that distributions, for some distribution and average distribution. Say if xk's are Bernoulli with parameter p, independent, so they are IID, then their sum will be binomial with parameters n, the number of xk's, and p. Well, we have used this. So Bernoulli p, if we are doing n times independent Bernoulli p, then the number of successes is binomial with np. And what about the distribution of xn? Well, the distribution of xn will not be, well, can be found, but will not be one of our standard distributions. Well, you just need to take the values of these binomial distribution values, divide by n. So binomial is taking values 0, 1, 2, etc. up to n. So our xn bar, if we will consider average will take values 0 over n, 1 over n, etc. n over n, with the same probabilities as binomial is taking its values. So not interesting to talk about the average of Sn, in fact, in this case. Okay, if xk's are binomial with parameter mp each and they are independent, then their sum will be binomial with parameters n times m, m times n, and p, probability is p. You can think like what is showing x1? x1 is showing m times repetition of some experiment with success probability p, independent. Then x2 is showing m times repetition, another m times repetition of the same experiment with success probability p, etc. So we are doing n times m times repetition. So we will have n times m times repetition of that experiment with success probability p, and Sn will calculate how many of the trials lead to success. Okay. Now, important cases when xk's are normal with mu sigma squared, with mean mu and variance sigma squared. If xk's are independent, then the sum of xk's will be again normal with parameter n times mu and n times sigma squared. So the mean will be n times mu and the variance will be n times sigma squared. So why is this? Well, of course we have talked about the sum of two normal random variables, but here if we will assume that, if we will admit that the sum is normal, then it is easy to calculate this. But another thing is to prove that the sum will be normal. This is the hard part of this of this statement. Sorry. Okay, now I am assuming that I know already that it is normal. I just want to find the mean and the variance. So how to find the mean? I will calculate the mean of this. So if I will calculate the mean of that is expected value of this, x1 plus etc. plus xn, then this will be the expected value of x1 plus expected value of xn, and the expected value of xn, the mean of xn is mu, so I will have n times mu. So that's why I am plugging here n times mu. Next, here I need to plug the variance of this. So if I have something like this, what I mean, if I have something like this, normal with some parameters, here I need to plug the mean of y, and here I need to plug the variance of y. So if I want to find this parameter, I need to calculate the variance of this. But the variance of sum of independent random variables is just the sum of variances. The variance of each xk is sigma squared. This is that variance. So I will have n times sigma squared here. And this was the distribution of Sn. And it is very important that in the normal case, the distribution of the average is again normal with parameters mu and sigma squared over n. Again, you can calculate in a similar way. The hard part is to prove that the distribution of this average is again normal. If we will assume that we know, we can easily calculate that parameters. You just need to calculate the expected value of this. Expected value will be mu. And the variance of this, we have calculated this kind of variance, and the variance of this will be sigma squared over n. Okay. So in these three cases, we know the distribution of either the sum or also the average. If xk's are Poisson with parameter lambda and are independent, then their sum will be again Poisson with parameter n times lambda. We have talked about the sum of two independent Poisson distributions in our previous lectures. And if xk's are geometric with parameter p and are independent, then their sum will be negative binomial with parameters n, p. N is the number of xk's, n and p. You can think about the interpretation of this easy to interpret if you will use the idea of normal binomial. What is counting that normal binomial random variable? Okay, in fact, there are a few others. Say, what will happen if I will add independent exponential random variables, etc. But only few these kind of results are known. Now let's go back to our general case. What we can say about the distribution of Sn and Xn bar, the sum and the average in the general case. So finding the distributions is very hard, but we can get some partial information very easily. Well, what is that partial information? Say we can calculate the expected value of Sn in any case. The expected value of Sn is the expected value of the sum, because Sn is this sum. And this is equal to, because we are talking about IID random variables, this will be n times the expected value of each of them. And we can calculate, of course, the variance of Sn. The variance of Sn is the variance of this sum, and because they are independent, now I am using independence. No independence is necessary here, but independence is important here. I will have the sum of variances. And the sum of variances, the variance of each is variance of x1, say. I will have n times the variance of x1. So I have this basic information about Sn. And I have the similar information about Xn bar. So if I will calculate the mean value of Xn bar, this is the expected value of Xn bar is equal to this, the average. So I can take out that 1 over n. I will left with this. So n times expected value of x1 over n, that will give expected value of x1. By the way, there is a, what this shows, well, I can read this as, this means that the mean of the means, so what I'm saying, the mean of the means, so this is the means or mean of this, the mean of the means is the mean, well, mean of x. Well, this kind of think about that. Okay, and what about the variance of Xn bar? Variance of Xn bar is variance of x1 plus xn over n. So I'm taking this out, 1 over n squared, this variance of the sum, and the variance of the sum is n times the variance of x1. So I will have the variance of x1 over n. Well, we have talked about this. The last property was the mathematical form of this proverb, Yotan kam chapir, mekan kam katrir. This is the mathematical statement. And the interpretation of these two, so the expected value of Xn bar is equal to expected value of x1, and the variance of Xn bar is variance of x1 over n, is the following. The values of Xn bar, so x1 is around that expected value of x1 if we are talking only about x1. It is around this because this is the mean of x1, and the variance is the variance of x1. x2 is again around this with the same variance x1, etc. If we will average x case and obtain Xn bar, then Xn bar will be around this number, the same number, is centered at that number, and the variance of Xn bar is going smaller and smaller. So Xn bar is becoming more and more concentrated around it than around this number as n increases. So the center is remaining the same if we are calculating the center of Xn bar, but the variance is tending to 0. So variability is tending, concentration is more concentrated. We are getting more concentrated numbers around that mean. And this relation is important in financial risk and investment theory. They are confirming the importance of diversification. We have talked about this. So expected, if we are talking about expected rate of return, expected return, then the variance is meaning the risk. If variance is small, then the risk is small. And diversification is saying that do not put all your eggs into one basket. Do not buy only one stock or one financial instrument. Diversify your investment into different stocks and different type of instruments to reduce the risk. Okay, so let's talk about the law of large numbers. Now we want to study some more properties of distribution of Xn bar or Sn in the general case. And we have two famous theorems, limit theorems in probability theory, law of large numbers, LLN, and the central limit theorem, CLT, that help us to get information about the asymptotic or limiting for large n properties of Xn bar and Sn in the general case, for general distribution behind x case, that random variables x case. So this is, we have two forms of law of large numbers, LLN. We have weak LLN, weak law of large numbers, and strong law of large numbers. They differ a lot. Well, there's a difference. Let me state that both, of course, for practical usage, they are the same. They are almost saying the same, but in mathematical terms, they are different. They are talking about different type convergences of random variables. Okay, so assume we have IID random variables, a sequence of IID random variables. They are independent, they are identically distributed with finite expectation and variance. In that case, the sequence of averages, so average calculated for the first n terms. So if n is increasing, then these averages are tending to the expected value x1 in the probability sense. So averages approach to expected value of x1 in probability sense. What it means that they are tending in probability sense, that means the following. This is the definition of that convergence in probability sense. So the probability that this will be far from that, so I'm calculating the probability that that average will minus that expected value in absolute value will be large, say from some epsilon. This tends to 0 when n is tending to infinity for any positive epsilon. So this means that for any epsilon, the chances that averages will be far from this expected value more than epsilon is very small. It's tending to 0 when n is tending to infinity. So this probability that this is far from that is small when n is large. The idea of the law of large numbers is the following. Let us denote by mu this expected value. We know that the mean of Xn bar is mu. So we have calculated the expected value of Xn bar. This is the same as the expected value of x1. This is mu. Is this enough to say that Xn bar is close to mu? Of course, no. This is saying that the average of Xn bar is mu, but nothing is about being close to mu. Well, we can have very far values with the mean mu. And what we need to have to say that Xn bar is close to mu. So we want to show under some conditions that Xn bar is close to mu. Only the mean is mu is not enough. So we need to have that the variance is very small. Variance is close to 0. If we will have that the mean is mu and the variance is small, then Xn bar is very concentrated around that mu. It's very close to mu. This is the idea. And we know that the variance of Xn bar, we have calculated the variance of Xn bar, is the variance of x1 over n. And this tends to 0 when n is tending to plus infinity. And this is what we wanted to get. This is the idea of the proof of weak law of large numbers. So rigorous proof of proof of this of this theorem is by using Chebyshev inequality, and it is almost one line. Well, I want to calculate this xn bar minus mu is larger. Mu is the expected value of x1. So I need to prove that this tends to 0. So I am using the Chebyshev inequality. First I'm writing this is equal to xn bar minus, well, mu is also the expected value of xn bar. So I need to have the same random variable expectation here to use that Chebyshev inequality. Xn bar is larger than, well, larger or equal than epsilon, larger than or equal to epsilon. So this is what we want to estimate. Sorry, my mouse pointer is not moving. Yeah, it is back, thanks. So by Chebyshev inequality, we will have that this is less or equal than the variance of xn bar over epsilon squared, this squared. And we have calculated, we have the variance of xn bar. This is sigma squared over n times epsilon squared. The variance of xn bar is sigma squared over n. Variance of x1 over n. And this tends to 0. So the statement is correct of that theorem. We have proved that statement. We have proved that xn bar is tending in probability, in the sense of probability, in this sense, to that mu, expected value of x1. This is the proof. Now the strong version of that law of large numbers. The strong version says that the above convergence holds also in the strong sense, under less restrictive setting. So if we have IID random variable sequence with finite expected value, only the expected value is finite, then this averages, sequence of averages, is tending to the same expectation, same EX1, almost surely, in the almost sure sense. So the statement is almost the same, but here, instead of convergence in the sense of probability, we have almost sure sense. And what this means? This means that this means that the probability that this is tending to expected value of x1 is 1. So it can happen that this is not tending to this at some omega, well, at some point, but the probability of that point is 0. So with one probability, we will have that this is tending to that. In the advanced theory of probability, one is proving that the convergence in the almost sure sense implies convergence in probability. But the inverse implication is not true in general. So if we have almost sure convergence, then we will have convergence in the probability sense. But the inverse is not true in general. So strong law of large numbers implies the weak law of large numbers. Another note is, well, it is not so easy to explain the difference between the convergence in probability and almost sure convergence in few words quickly. But in fact, it can happen that some sequence yn of random variables tends to y in probability, but at no point yn tends to y in our ordinary sense. So maybe yn is tending to y in probability, but not in the ordinary sense. Well, another note, assume that g is continuous function, then one can prove that under the conditions of strong weak law of large numbers, g at this point is tending to g at the expectation. Well, it seems so trivial. If this tends to that, then g of this tends to g of that. This is by continuity of our function g. Well, this is in fact trivial for the almost sure convergence, but maybe not so trivial for the probability sense convergence. If we have that this tends to expected value in probability sense, then one needs to prove that g of this tends in probability sense to g of this expected value. Say, let me open something, a whiteboard, and write. Say if we have this kind of thing, plus xn over n, and we are given the following question: calculate what is the limit of this in the sense of probability or in the almost sure sense. Then we will write by weak or strong law of large numbers, either in the probability sense or in the almost sure sense. This is tending to, because this tends to expected value of x1, this is the statement of our law of large numbers. We will get that this tends to this cubed, expected value cubed. Okay. Now, in other questions, in other problems, we will be required to calculate this kind of limit in the probability or almost sure sense for some nice function g. If we will have that expected value of g of x1 and the variance of g of x1 are finite for convergence in probability, or just this is finite for the strong law of large numbers if we want to calculate in the almost sure sense, then we will have the following. So think like this. This is y1. Say I am denoting this by y1. This is y2, etc. This is yn. Because xk's are iid, they are independent, say, then y1, y2, etc. yn will be independent. Because they have the same distribution, x1, x2, xn have the same distribution, then y1, y2, etc. yn will have the same distribution. So these yk's are iid. Then by the law of large numbers, either weak or strong, we will have this tends to expected value of y1. And expected value of y1 is the expected value of gx1. So this is tending, the average of gxk is tending in the almost sure probability sense to the expected value of g of x1. So, by the way, important thing, this is xn over n, different from this. This is the theoretical mean for random variable x1. This is the average or sample mean of x1, x2, xn over n. So this is a number, expected value is a number. This is a random variable. Please do not confuse this with that. And the law of large numbers says that these random variables, depending on n, if we are increasing n, we are calculating different random variables here. So these random variables is, the sequence of these random variables is tending to this number when n is tending to infinity. This is the statement of that law of large numbers. Okay, an example. Assume we have random variables, well, infinite many of them, from uniform distribution on -1, 2. We have they are independent, well, identically distributed because they have the same distribution, uniform -1, 2. So we are asked to calculate in one of these senses the limit of this. Well, of course, in both senses, the limit will be expected value. So here, in the first case, by weak or strong, sorry, let me just write law of large numbers. By the law of large numbers, this will tend to the expected value of x1. And how to calculate the expected value? Well, very easy, because we know the distribution. This is the midpoint of this. So -1 plus 2, 1 over 2, 1 over 2. So this sequence of random variables is tending to 1 over 2, this number. Now, how to calculate this? Again, by the law of large numbers, this is equal to the expected value of just x1 squared. We have, this is our y1, y2, etc., yn over n. These are independent IID, y1, y2, yn are independent. Then the law of large numbers says that this tends in this sense or that sense to expected value of y1, that is expected value of x1 squared. How to calculate the expected value of x1 squared? Well, two methods, either to integrate x squared times the PDF, or just write the variance of x1, because we know the variance of this random variable, plus expected value of x1, this squared. And the variance of x1 is the variance of uniform minus 1, 2 random variable. B minus a squared, so 3 squared over 12. This is the variance for uniform, and plus, well, the mean value, which is 1 over 2 squared. So this sequence of random variables tends to this number by the law of large numbers. Okay, and how to calculate this? Again, this is our y1, y2, yn, n random variables over n. So this is the average of that random variables. They are independent and identically distributed. So this tends by law of large numbers to the expected value of e to the x1. And this is, now I need to use integral for calculating this. This is the integral from -1 to 2 of ex times the PDF. PDF is 1 over 3 in this interval and 0 otherwise. So I will calculate this integral, and this number is the limit of this sequence of random variables. Assume we have a coin for which the probability of having heads is p. We are tossing that coin many times independently. We calculate the proportion of heads for that tosses. So how many times we had heads over the total number of experiments. What is the limit of that proportion in almost sure sense if we repeat tossing infinitely many times? If we will repeat tossing, then calculate what is the proportion of heads limit, then we are required to calculate that proportion. Well, in fact, we will have this p. This p is the limit of that proportion. Let's see why is that. So let x1 be 1 if heads and 0 if tails in the first toss. And similarly, let me just write xk. xk is 1 if I have heads in kth toss and 0 if tails in the same toss, kth toss. Then, of course, xk's are Bernoulli with parameter p, because the probability of 1, probability of heads is p, Bernoulli p. And xk's are independent because I am doing my tosses independently. So xk's are IID. They are identically distributed because they have the same distribution, and they are independent because I'm doing that trials independently. Okay. Now, how to calculate what is the proportion of heads in that case? The proportion of heads in n trials. I want to calculate what is the proportion of heads in the first n trials. This is equal to the following. I need to calculate how many heads I have in that n trials. And that how many heads is just this number, the sum, sorry, is just this sum over n. So I will have either 1 or 0. The number 1 will show that I have heads, so the number of that ones will show how many heads I have in that n tosses. So this will give the ratio of number of successes over n. This is the proportion of heads in n trials. And by, well, I need to use strong law of large numbers. In almost sure sense, this will tend to expected value of x1. x1 here. So what is the expected value of x1? The expected value of x1 is the expected value of this Bernoulli random variable, Bernoulli p, and this is p. So proportion of heads in n trials is tending to p. So if, say, explanation of this, if we have fair coin, then if we will, say, toss it 1 million times, then we will have almost half of them heads, show heads. So the proportion of heads will be almost 1/2 in that 1 million. And if I will increase this number, that proportion will approach to that exact 1/2. Later, I will add some video how to visualize, how to experiment in R to show, to interpret that, to show how law of large numbers and central limit theorems are working. But here, let's talk about the theoretical part and practical calculation part, solve some problems about the theorems. Okay, this example is the base of frequentist interpretation of the probability. So frequentists interpret the probability of some event is P like this. The probability of an event is P can be understood as the following. We repeat that experiment many times independently and calculate the proportion of times we will have that event happening. Then the limit of that proportion is exactly P. So this is that frequentist interpretation of probabilities. And there is another one, say, Bayesian interpretation of that. You can read about that in textbooks or in other media. Okay, so the next example is the following. Assume g is continuous function defined on AB, and we want to calculate the integral from a to b of g of x dx. Well, you know some tools to calculate, some methods to calculate explicitly. Assume this is some function you cannot calculate by hand. You can use some numerical methods, you know. Well, okay, many numerical methods will work, but I want to use another method. I want to use that law of large numbers or Monte Carlo method to calculate this integral. In fact, for this one-dimensional case, maybe that numerical methods will work pretty well, and maybe this Monte Carlo method will not give too fast convergence to a nice, better result than that numerical method, say Simpson method or other methods of quadrature. But in the multi-dimensional case, this Monte Carlo method will work nice even if that numerical methods will not work because of that curse of dimensionality. Okay, so let's see how we can calculate this integral. First part is the following. Prove that if x1, x2, etc. So, by the way, sorry, nothing probabilistic here. We have some function, a, b numbers over some interval, and we want to calculate this number. Nothing probabilistic. Now we are doing the following. We are taking IID random variables with uniform distribution in this AB. Then we are calculating the average value of these numbers, g of x1, g of x2, g of xn over n. So we are calculating this. Then this is tending almost surely, or in probability sense, here I'm talking about almost sure convergence. So this is tending to this integral times 1 over b minus a. So let me show this, let me prove that, and then calculate in R this integral. Well, you can try by yourself. Can you calculate this integral in other way, say by hands or by using some numerical methods? And I will use this method, Monte Carlo method, to calculate this interval, basic Monte Carlo method to calculate this integral. Okay, first part, I want to prove this. I'm doing the following. So, g of x1 plus g of x2. My aim is to calculate the limit of this average, g of xn over n. So, by the law of large numbers, strong law of large numbers, if I am talking about almost sure convergence, this will tend to, now this is my y1, y2, yn. Y1, y2, yn are IID again, because xk's are IID. Then g of x1, g of x2, g of xn will be IID. So this will tend to the expected value of this random variable, g of x1 just. Now I have that xk's are, I have the distribution of xk's, uniform from A to B. If I know this, then I can calculate this expected value, and this expected value will give g of small x from minus infinity to plus infinity times the PDF of x dx. But the PDF of uniform distribution is 0 outside of this interval and is 1 over b minus a on that interval. So I will have just integral from a to b, g of x times 1 over b minus a dx. This will go out and we will obtain that property we wanted to prove, that number. So we can calculate the integral of g by calculating this for large n and by multiplying by b minus a. So integral from a to b of g of x dx is approximately, when n is large, n, oh, not n, sorry, this was correct, n is large, well, yeah, n large, this is b minus a times gx1 plus etc. Well, let me erase maybe this part. Okay. So this is equal to, this integral is almost equal to b minus a times this. So g of x1 plus g of x2 plus g of xn over n. Okay. By the way, you can find some similarity with the definition of the integral itself. So how we are defining that integral over AB of g? We are dividing this interval into small parts. We are taking some number from each part. We are multiplying by the width of this interval, adding that numbers. Something like that, but here, instead of deterministic points from each interval, we are taking random uniformly generated numbers here. You can think about that. Okay, so I'm erasing this and going back to our lecture, and I want to calculate this integral in R. Integral from 0 to 2 sine of x times e to the minus x squared dx. Okay, let's go to our R. This is not our R, this is our R. Okay. Now I'm first defining my function. Our function is So defining function is just writing function of x. Return. Yes, return. Function was sine of x times exponential minus x squared. Yeah. And I'm running this, Control Enter. Yeah, I have that function. Okay. Now what I'm doing, I'm generating my AB. A was 0, B was 2. I want to integrate from A to, well, I have not, well, let me run that. Now I have A and B and our function. I want to integrate over AB. To that end, I'm taking some n, the number of points I will generate, say 100 points first, then I will increase that number. If n will be large, I will get more and more precise close values, a nice approximation for the integral. Now I'm generating uniformly distributed random numbers from A to B, so R unif. I want to have n numbers from A to B. Okay, I have some numbers from A to B. Now what I'm doing, I just calculate the function value at that x. So this will give f at x1, f at x2, f at xn, etc. Then I need to average these numbers. So averaging is very easy. I'm just writing mean of this vector. The average of that vector, sorry. Yeah. So this is the average. This is instead of g of x1 plus g of x2 plus g of xn over n. And we need to multiply by, so we need to multiply by b minus a. If you remember, that integral value was b minus a times that average. So I'm running this and I am obtaining 0.406. Now let me use integrate function of r to integrate that function. So f lower upper limit, so from a to b, just give me that integral. 0.42 with error something e to the 10 to the minus 15. Okay, so let me do the following. Now let me increase. We have obtained it, of course, 0.4. It is not so close, but let me increase that numbers. Say 10,000. I'm running this, generating again, calculating these numbers. You can see that I have close value to the actual integral value. Okay. This is because of that law of large numbers. You can see. Okay. So why the idea of casino works and why the idea of insurance work? Sometimes casino and insurance companies will pay a lot of money to their customers. So why their job is profitable? This is because the idea is because of the law of large numbers. And you cannot run away from the fortune, from the math, from the law of large numbers. In the long run, casino and insurance companies will win. This is the idea. How to explain this? Let me give just one example. Consider, say, an American roulette game. The American roulette game. We have 38. We have talked about this. We have solved the problem about that. But let me repeat quickly. We have 38 pockets, numbers from 0 to 36 and 00. These two are in green. The half of others are in red. The other half is in black. So one of the betting methods is to bet on the color, either on black or red. Say a person is winning $1 if he is correctly guessing that color, and otherwise he is losing that $1. We have calculated the expected winning of that person. Expected winning is minus 1 over 19, which is the same from the point of view of casino. Expected gain of casino from that person will be 1 over 19. Gain is the gain from that person's game of casino. Gain of casino from that person's game. Okay, what this means, how to interpret this. Well, assume G1 is the gain of casino from the first person, G2 from the second person, etc. GKs are random. IID. Why IID? Well, they are independent. The first person's winning or lost money is independent of the second person's. Well, we assume that. And they are identically distributed. They are all coming from some hypothetical distribution of gains from person. Okay, well, of course it can happen that in some scenario the first person will win, the second person will win, etc. The 15th person will win, and the gain of casino will be -1. Well, this is of course possible. But now let us consider what we will have in the long run. We consider n players. Then the total gain of casino will be the sum of particular gains from the first person, second person, nth player. The law of large numbers says that this average will tend to the expected value of G1. So it will tend to the 1/19. So for large n, this will be close to that. So for large n, the total gain, that is this sum, will be approximately n times this. So this means that even sometimes casino will pay to players in the long run. Then, even sometimes casino will pay to players, but in the long run for many players, casino will win. So it will have almost n/19 from n persons. That's why the idea of casino works. The same works also for insurance companies. They are making, they are taking premiums for insurance contract. You say you pay some money for insurance contract, and they are calculating that premiums, that money, how to pay for that contract in such a way that the expected gain of the company will be positive. Sometimes they will pay for some accident, etc. But if they will have a lot of customers in the long run for large n, they will win. Their winning will be positive. This is because of this law of large numbers. Okay, this much about law of large numbers. Let's talk about the central limit theorem. First, a reminder about standard normal random variables. So assume Z is standard normal, then we are denoting by capital Phi the CDF of that standard normal, and by small phi the PDF. So this is the PDF for standard normal with 0, 1 parameters, and the CDF is just the integral of this. This integral is not cannot be expressed in the elementary functions form, so we are writing I'm just writing in this way. And the probability that Z is between A and B is calculated by the CDF value at B minus the CDF value at A, and we can calculate these two numbers either by standard normal tables or just by using some software, R say. Now let's consider the average of x1 to xn. The law of large numbers says that the values of xn bar are concentrated around expected value of x1 if n is large. So if n is tending to infinity, this tends to this number. These random variables tend to that. So that means that these numbers are concentrated around that. But law of large numbers is not giving idea about the distribution, of these numbers. So we know that these numbers are close to that, but what is the distribution? The means of these numbers is this, and the limit of this distribution is this. But what is the distribution of these average values around that mean? And CLT is about that distribution of xn bar. So CLT is giving the asymptotic distribution of xn bar, and also for the sum Sn. not only the average but also the sum. So we called it Galton board. We were obtaining the distribution of balls over the long run, over large N. So we will use standardization idea. I'm just recalling what is the standardization of a random variable. Say we have a random variable x minus expected value of x over the standard deviation of x, or the square root of the variance. I'm using square root of the variance usually, not the standard deviation, but this is called the standardization of x. And we have two properties. The expected value of y is 0 and the variance of y is 1. And in general case, y is not normal. Y will be normal random variable if and only if x is normal random variable. So, but what we have, so I cannot write that y is normal with 0, 1 parameters. I can just write that the mean of y is 0 and the variance of y is 1. In general case, in general x, for general x. Okay, so what is the basic idea of central limit theorem? If we have a sequence of IID random variables xn with finite expectation and variance, and we consider their sum Sn or their average Xn bar, then for large n, the standardized Sn or standardized Xn bar are approximately normal 0, 1 distributed. That is, this random variable, this is a random variable because Sn is a random variable, this is a number, expected value, this is a number. So we are standardizing Sn, we are obtaining this random variable. This is approximately normal 0, 1 distributed. So for large n, this is almost normal 0, 1 distributed. The shape will be close to that normal. And if we will, similarly, if we will standardize Xn bar, so Xn bar minus its mean over the standard deviation of Xn bar, this is approximately normal 0, 1 distributed. This is what is the meaning of what is the idea of CLT. And this holds for any IID sequence xk coming from any distribution. Not important the distribution behind xk. Important is that xk have finite expectation and variance. So if we are adding that random variables xk and standardizing, we will have normal distribution. So in fact, Sn will be almost normal with some mean and variance, and Xn bar will be almost normal for large n with some mean and variance. We will talk about that interpretation later. Okay, now let's talk about the rigorous statement of CLT, first in the sum form for Sn. So Xn is a sequence of IID random variables with finite expectation mu and variance sigma squared, variance of xi. We consider these sums. Sn is the sum of first n terms. And we standardize Sn. We denote by Zn the standardized version of Sn. So Sn minus its expectation over the standard deviation of Sn, that is square root of the variance of Sn. Now if we will use the expected value of Sn, if we will calculate the expected value of this, will be sum of expected values, and because each expected value is mu, we will have n times mu. And the variance of this will be n times the variance because of independence. We have IID random variables. Variance will be n times sigma squared. Then we can write Zn is this ratio, Sn minus its mean over square root of the variance of Sn. Then CLT, central limit theorem, states, for any AB, as n is tending to infinity, the probability that this standardized random variable is between A and B is tending to the probability that standard normal Z is between A and B. Z is standard normal. So I can calculate this because Z is standard normal. I can just use phi of B minus phi of A. Phi is the CDF of Z. And this works for any Zn, any random variable, standardized sum of random variables. That is, if I am plugging this value of Zn, the probability that standardized sum is between A and B tends to the probability that standard normal is between A and B. Usually people in textbooks you will find in this form. Sometimes textbooks are using sums form Sn, they are writing for Sn. Sometimes they are writing for Xn bar, the average form. We will talk about the difference between that two statements. So this is for sums Sn. I am not plugging that values because every time I will calculate, I do not want to let you remember by heart. Not necessary to remember this. The idea, if you will get the idea what to do, so you need to form the sum. This is the sum. You need to standardize that. That means to calculate this and calculate this central limit theorem. That's why I'm keeping in this form, not writing in this way. So I will solve some problems for you and you can see how I am using that. Okay, so next is CLT in the averages form. So for Xn bar, assume Xn are sequence of IID random variables with finite expectation mu for each random variable and finite variance for each random variable. We consider these averages. We standardize these averages, we denote by Zn Xn bar minus its mean over square root of the variance of that mean. So standard deviation of that Xn bar. I can calculate this, we have calculated of course that expected value of this will be just the expected value of x1, which is mu, and the variance of this we have calculated several times. We've talked about that several times. The variance of this will be 1 over n times the variance of x1. So sigma squared over n. Now we can write this ratio, the standardized random variable Zn, as Xn bar minus mu, this is mu, over, this was sigma squared over n, so we will have sigma over square root of n. And you will meet in many textbooks when talking about CLT this ratio. So CLT states, for any A and B, as n tends to infinity, the probability that Zn is between A and B, this is Zn, is tending to the probability that Z is between A and B. Z is standard normal. We know how to calculate this probability, this number. Then we will be able to approximate this. Or if I will plug the value of Zn, I will have the following. Probability that A is, this is between A and B. A is less or equal than standardized Xn bar is less or equal than B. This is tending to probability that Z is between A and B. Z is standard normal. Okay. Relation between two versions of that CLTs. It is easy to see that the standardized version of the sum is the same as the standardized version of averages. Well, I was denoting this by Zn because these were the same. Okay, that is Sn minus n times mu, this is n times mu, over square root of n times sigma, is Xn bar minus mu, this is mu, over sigma over square root of n. How to prove that? Well, Sn is the sum of Xn's. I am taking out that n times Sn over n minus mu, this is the same as that, over square root of n times sigma. Now, Sn over n, Sn is the sum x1 plus x2 plus xn over n. So this is Xn bar exactly. Here we have Sn over n minus mu over, I'm cancelling square root of n, I'm writing in this way. So this is Xn bar minus mu over sigma over square root of n. Well, sometimes people are taking the square root of n to the numerator, but I am not doing that. So I'm writing in this way. Usually I'm using this expression or that expression for the CLT. to not to remember this formula, but to obtain that formula. I can obtain that every time. So hence the above two versions of CLT are the same. Just one is in terms of Sn, the other one is in terms of Xn bar. The CLT is talking about this random variable, and it is saying that this random variable is approximately standard normal 0, 1. Now how to use that CLT? CLT says that the standardized random variable Zn standardized from Sn or Xn bar will have this property for Z, where Z is normal 0, 1. We use this in the following form. For large n, usually in textbooks you'll find this kind of thing. You can use this CLT if n is approximation, if n is larger or equal than 30. So probability that Zn is between A and B is almost can be approximated by probability that Z is between A and B. And the probability that Z is between A and B is the CDF of standard normal at B minus CDF at A. And we know how to calculate these values. So we can approximate this probability. So let me give more precisely, then I will give some examples. So example, assume we have IID random variables and we want to calculate approximately this probability. We just know the expected values, we just know the variances, but we do not know the distribution. We want to estimate this. We will calculate approximately. Assume we know only this and that. Finding a distribution is impossible because we do not know the distributions of xk's individually. Okay, we need to rely on CLT. What are we doing? So we are denoting by Sn this sum. Well, we want to calculate this probability. Sn is between A and B. CLT was about standardized sum. So we need to standardize this Sn. So I'm doing some calculations to obtain some transformations maybe to obtain standardized Sn. So to that end, I need to calculate Sn minus expected value of Sn over square root of the variance of Sn. And because I want to have the same probability, my aim was to calculate this. I'm doing the same transform with A and with B. So from all sides, I'm extracting expected value of Sn, and I'm dividing by the square root of the variance of Sn, by standard deviation of Sn. So this is equal to that trivially. Well, you just cancel and you get back to this. But how this is helping? Now this part, well, this part is exactly the standardized Sn, Zn. And the central limit theorem says, if you have something with Zn between some two numbers, then this is approximately equal to the same probability but with Z here, and Z is standard normal. So let's see what is written here. Yeah, so CLT says this probability we wanted to calculate is approximately the probability with, instead of this Z. We are writing instead of this Z. Z is standard normal. Now, we know how to calculate this expected value. This is a number. A is given. So we can calculate this. Variances can be calculated through variances of xk's. We have variances of xk's, so we can calculate this. So we will have this number. We will have this number. And Z is standard normal. We can calculate this probability. Then we will approximate this initial probability. This is the way we are using that central limit theorem. And we can calculate this probability. Yeah. Now another example. Say, assume about the average. Assume we have IID random variables x1 to xn. We have the expected value, variance for each. And we want to calculate approximately that xn, this average xn bar is less or equal than b. Again, we do not know the distribution of this to calculate, so we need to use that CLT. So we cannot calculate this by using CDF, PDF, PMF in general case. Okay, we are using CLT. To that end, we are denoting by xm bar this. So we want to calculate the probability that xm bar is less or equal than b. Now we are standardizing that xm bar. So xm bar is less or equal than b can be written in this form. So to standardize, I need to extract that, subtract expected value of that xm bar and divide by standard deviation of xm bar. So this is the standardized version of xm bar. Because I want to keep the same probability, I'm doing the same transformation with the right hand side. So this is equal to that trivially. Now what is the meaning of doing this transform? The meaning is that this is Zn, which is standardized version of averages, and the CLT is saying this is approximately equal to, instead of the Zn, plug Z, and Z is standard normal random variable. So, yeah, we can calculate this having the expected value of x1, x2, xn. We can calculate the variance. So we will calculate this, and finally we will calculate this probability because Z is standard normal. We know how to calculate this type of probability. This will be the CDF of standard normal at this point. Okay, an example of usage of CLT. Assume I have a piggy bank, in Armenian Hayren Kassa. Well, I'm collecting coins, 500 AMD coins in my piggy. The mean weight of that 500 AMD is 5 grams. This is from Wikipedia. With standard deviation 0.1 grams. Well, this is from me, myself. I do not know the exact standard deviation of that, so I'm assuming it is 0.1 grams. Around that 5 grams. Not every 500 AMD coin will weigh exactly 5 grams. So in the mean it will be 5 grams, but we'll have some distribution around that. I'm assuming that standard deviation is 0.1. I'm not assuming that the distribution is normal. I'm not assuming anything besides these two. Mean is 5 grams and standard deviation is 0.1 gram. I have collected 250 coins. So I'm rich. Okay. Assume W is the weight in grams of total that 250 coins. So what is the probability that W, the weight, total weight, will be larger than 1248? Oh, this number. Or second part is, what is the probability that W is between these two? Well, if I have 250 coins, every coin is average weight, every coin is 5 grams in average. Then in average I have 1250 grams. But some coins will be heavier, some lighter, so I want to calculate what is the probability of this. Okay, to solve this I'm using CLT. So let me denote by x1 or xk the weight of k's coin. And I have 250 coins, so 250. K is running from 1 to 250. Okay, xk's are IID. They are independent. Well, the first coin's weight is not dependent on the second coin's weight. Well, I'm assuming that. And they are identically distributed. They are all coming from the hypothetical theoretical distribution of weight of a 500 grams coin. Okay. Now, what I have about xk, I have that the mean value of xk, mean weight is 5 grams in grams, and the standard deviation, well, sigma is, this is mu, this is sigma, sigma is 0.1 grams. Now W, I need to calculate this probability with W. W is the weight in grams of all that coins. So W is just the sum of the weights. X1 plus etc. plus X250. So this is, in our terminology, this will be the average of 250 X bar 250. Okay, so now we want to calculate this probability. The probability that W is larger than that number, which is the same as the probability that X250 bar is larger than that number. So what I'm doing here at this moment, I'm thinking about, let me write it here. So I have reduced to this problem. So standardize. What it means? Make transformation such that you will not change anything here, but you will have standardized version of this. So I need to extract the mean minus the expected value of that X250 bar. So I am doing the same here. I will complete this. I am keeping that unfinished yet. So expected value of this X bar 250 over the square root of the variance of X bar 250. Well, I'm not writing correctly, sorry. So instead of X bar, this is not X bar. W is, sorry. W is the weight, total weight of 250 grams. This is not the average. This is X1 plus X2 plus etc. plus, plus X250. This is not X bar, but S250. Sorry for that. I will correct. So I'm correcting this. I'm erasing and writing the probability that W is larger than 1248. This is the probability that S250 is larger than 1248. And now I'm standardizing. Sorry for that again. So probability that S250 minus, I need to subtract the expected value of that, the mean value, then divide by the square root of the variance of S250. This is larger than, I'm doing the same transform with that. So that number minus expected value of S250 over square root of the variance S250. So in fact, this and that is the same. Now I'm continuing from this point. This is the place where I am using the central limit theorem. Central limit theorem says, take normal 0, 1 random variable, then this probability, this is our standardized random variable, this is just a number. This probability is almost equal to, I'm continuing from this point, so this is almost equal to the probability. Instead of this, I'm plugging that z. And the rest is just calculation of probabilities. Well, calculation of these numbers and probabilities. Square root of variance of S250. Okay, I have reduced to something I can calculate now. Let me calculate. To calculate this, first I need to calculate the expected value of Sn. Well, this was 250. Expected value of S250. So S250 is just the sum of first 250 elements of xk, x2, weights of our coins, x250. So this is equal to 250 times the expected value of x1. And the expected value of x1 is 5 grams. So 1250. Okay. And what about the variance of S250? This is the variance of this sum. Because of independence, I will have sum of variances, and the variance of each will be 0, 1 squared. This is the standard deviation. So variance is 0, 1 squared. So I will have 250 times 0.1 squared. Now I am plugging these values here. So I will erase this and plug it here. So I am erasing this to have a space. Now I am plugging that values. This is the probability that z is larger, 1248 minus 1250 over square root of 250 times 0, 1 squared. Well, let me just simplify this. Z is larger than minus 2 over 0.1 squared. I will have 0.1 square root of 250. Well, let me keep in this way. So to calculate this probability now, to use that CDF of standard normal, I just write it in the following way. 1 minus probability that z is less or equal than that. So probability that z is less or equal than some number is the CDF value at that number. Minus 2 over, well, 2 over 0.1 will be 20 over square root of 250. Now I need to calculate just this number, this probability, minus 1 minus the CDF of standard normal at minus 20 over square root of 250. Let me do that in R. So going to R, sorry, something is not working. Yeah, let me erase this. Now it is working. So first I'm calculating that number, say minus 20 over square root of 250, and I'm calculating 1 minus CDF of normal, P norm. Because I'm using standard normal, I'm not giving any parameters, I'm just writing at A. So the probability is 0.89 or 90, 0.9, almost 0.9. So the first part is, this is almost 0.9. Okay, so calculate approximately the probability that W will be between these 2 points, including this and not including that. Okay, I'm doing the same thing. So I'm writing this in the form of, well, my W is the sum of x1 to x2 to x250. So I can write in the form of a sum less or equal than S250. This is less than 1260. The next is standardizing. Standardize to use CLT. So what I'm doing, I'm extracting from both sides the mean of this minus expected value of S250. Well, we know this value, but I'm writing in this way to show the standardized version of that. This is 2 over square root of the variance of Sn. This is less or equal than S250 minus expected value. This is the standardized version of S250. So this over square root of that variance. And this is less than 1260 minus expected value of S250 over the square root of the variance of S250. And now I'm using at this point exactly, I'm using the central limit theorem. So central limit theorem says that this is approximately, so this is approximately equal, taking some standard normal random variable z, this is approximately equal to the following. Instead of this, I am plugging exactly z. So let me calculate. So 1240 minus 1250, we have calculated that. The variance of Sn was 0.1 times square root of 250. This is less or equal than z, and this is less than the same but with 1260 over 0.1 times square root of 250. This is the approximation of this integral. This is the not integral, probability, sorry. This is the approximation of this probability. Now we can calculate this last probability. Because z is standard normal, I just need to calculate that left and right side numbers. This is minus 10, so this will be probability that this will give minus 10, so minus 100 over square root of 250 is less or equal than z, and this is less than, here I will have 10 over 0.1, so 100 over square root of 250. This is the value of CDF at this point, 100 over square root of 250, minus the CDF at minus 100 over square root of 250. And I'm calculating this by using R. So going to R, I'm calculating the following. So P norm, yeah, at the point 100 over square root of 250 minus, well, I can copy this, Control C, Control V, and add minus sign here. And run this, that will give 1. Well, very close to 1, because this is very, these numbers are very far from 0. So we will have, this is almost 0, this is almost 1. So the difference is almost 1. Okay. This much about this example. Let's continue. The length of rods produced by a machine have a mean 100 centimeters and standard deviation 5 centimeters. Find the probability that if 60 rods are randomly chosen from the machine, the mean length of the sample will be at most 101 centimeters. So we are modeling this. So let's denote that 60 rods lengths by, say, x1. This is the length of the first rod, x2, etc. So xk is the length, xk is length of kth rod. What we know about xk, I do not know the distribution, but I know that the expected value of xk is 100. Expected length is 1 meter, 100 centimeters, and the standard deviation of xk is 5 centimeters. So the variance of xk is 25 centimeters squared. Let me just erase this. So I want to find the probability that if 60 rods are randomly chosen, then the mean length will be x60 bar. So mean length of that sample will be at most 101. So we want to calculate the probability that that mean length is less or equal than 101. So the previous problem was about the sum of random variables. Here, the problem is about the average of random variables. Now, I'm doing the same thing. So first standardizing that xm bar, x60 bar. To that end, I'm extracting the mean of that and dividing by the standard deviation or the square root of the variance of that, 60 here. Doing the same with the other side, minus the expected value, x60 bar over square root of the variance, x60 bar. Now, at this point, we are using the CLT. CLT says if you are standardizing, then for large n, well, 60 is larger than 30, so we can use, if we will take normal 0, 1, standard normal random variable, then we can approximate by probability that instead of this I am writing z, and I'm keeping that number. 101 minus expected value of x60 bar over the standard deviation of x60 bar. Well, here I have, okay, let me erase and write it here. Sorry. Where is this line coming from? Okay, so by CLT, we will have for z from normal 0, 1, we'll have the following. This probability is approximately probability that z is less or equal than 100, this was 101, 101 minus the expected value of x bar 60 over the square root of variance of x bar 60. 60 bar. Now I'm calculating these numbers. So I'm erasing this to have a place. Expected value of x60 bar is just expected value of, oh, sorry, no need to write that bar. Expected value of, okay, every time I'm erasing, this program is making symbols unreadable. Sorry for that. So expected value of x60 bar is just expected value of each of x case, x1. So this is 100. And the variance of x60 bar is the variance of 1, we have used this formula a lot, over n over 60. So this is equal to 5 squared, 5 centimeters squared over 60. So I'm plugging that here. Let me erase this and use that numbers. So this is equal to the probability that z is less or equal than 101 minus the average is 100 over square root of variance 5 squared over 60. So I will have probability that z is less or equal than 1 over, or this square root of 60 will go up. So square root of 60 over 5. And I'm calculating this probability by using the CDF phi at square root of 60 over 5. So what is the probability if we will randomly choose 60 rods and the mean length of the sample will be at most this is, now I will calculate that by using R. So it was P norm at the point square root of 60 over 5. standard normals CDF, so I'm not writing any parameters. 0.94. Okay. So again, going back to our CLT statement, in a non-rigorous way, we can write for large n. Here, approximately means approximately distributed as, because we are talking about random variables. Writing this will mean that it is approximately distributed like. So the standardized version of sums, Sn, is approximately distributed as normal 0, 1. And the standardized version of averages is approximately distributed as normal 0, 1, standard normal 0, 1. This is the, roughly, this is the statement of our central limit theorem. Very easy to remember. And if I will do calculations, so if expected value of x1 is mu, I will denote by mu. And if variance of x1 will be denoted by sigma squared. So this is sigma squared, well, not this, but we will calculate this by using this sigma squared. We are using the sigma and mu for x1. Then the expected value of Sn will be n times mu. Expected value of sum is n times the expected value of each, n times mu, over square root of this will give square root of n times sigma if you calculate this variance. So this is approximately normal 0, 1. And if we will calculate this and that, well, this was mu, and this was sigma squared over n, variance of x1 over n. So I'm writing sigma over square root of n. So this is approximately normal 0, 1. So what is giving this? Here I can write the following. Sn minus n mu is approximately square root of n times sigma times normal 0, 1. And we remember that if we will multiply normal 0, 1 by some number, I'm multiplying here by that number and I'm getting normal 0 and square here. So n sigma squared here. And if I will take this to the other side, I will have Sn is approximately n mu plus this normal 0 and sigma squared. So this means if I'm adding some number to normal distribution, I will get normal with this mean n mu and n sigma squared. So I know the approximate distribution Sn. It is approximately normal with n mu and sigma squared. So I'm erasing this and showing what I have in the slides. So if we will do that kind of calculations, we will have Sn is almost normal n mu and sigma squared, and xm bar, if we will do that calculations here, is almost normal with mu sigma squared over n. This is that implication of our central limit theorem. If you will generate a lot of samples from distribution of x, any distribution with two parameters mu and sigma squared in R, so you are doing in R, and you will construct the histogram of Sn, that is approximate the distribution of Sn, you will get very close bell-shaped curve to this. So if you will draw the histogram of this and PDF of this, you will get nice agreement if n is large. And maybe this is better to visualize because this, if n is large, this will be large. If mu is non-zero, maybe this is better to visualize. If you will take a lot of examples of xm bar, if you'll do the histogram, then that histogram will very nicely agree, if n is large, to the PDF of this random variable. Try to do that experiment by yourself. And summarizing, comparing with normal, if xk's are independent with min mu, variance sigma squared, and are normally distributed, this is important. If they are normally distributed, then xk, that is xk is normal with mu sigma squared, then Sn is exactly normally distributed with n mu and sigma squared. We have talked about this in the first part. And xn bar is normally distributed with mu, sigma squared, and exactly. This is the case when xk's are normally distributed. And if xk's are independent, again, have the mean mu, variance sigma squared, but from any distribution, maybe not normal, then Sn, the sum, is approximately normal with the same parameters, and Xn bar is approximately normal with these parameters. And we know the asymptotic distributions, approximate distributions of Sn and Xn bar. So this is the meaning of central limit theorem, and this is why normal distribution is very important and very much happening in applications. So if you have sum of independent things, if you have average, if you are calculating average weight, average height, etc., then you will have approximately normal distribution, and you can calculate with normal distributions CDF. Okay, this much. Thanks a lot. Have a nice day. Bye.